Pluto, a far-off and confounding body, was once viewed as a solitary and real planet, a member of our planetary family. However, recent unsettling statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an astonishing revelation. They propose that this cold world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such a giant event? Are we witnessing a fascinating cosmic anomaly, or is there more to this looming astronomical incident? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was relegated to a lesser status, remains a subject of fascination and study in the astronomical community. According to detailed calculations by leading experts, Pluto's orbit is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are raising the alarm about a potentially dangerous calamity between these two celestial bodies, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's orbit around the Sun is unusual compared to other planets in our solar system. It takes an astonishing 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full trip around the Sun. However, the intrigue doesn't stop there. Pluto's orbit is characterized by its highly eccentric shape, vastly different from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination of 17 degrees to the ecliptic plane. This means Pluto follows a far more erratic path compared to other planets. This inclination and eccentricity add layers of complexity to its orbital behavior. Perhaps one of the most captivating aspects of Pluto's orbit is its interaction with Neptune's orbit. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, contrary to what one might expect from their positions in the solar system. This raises the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational interactions of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers sought to explain its peculiar trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and erratic shape. The mystery of Pluto's orbit can be explained by the three-body problem in celestial mechanics. This involves understanding how three objects in space, like Pluto, Neptune, and the Sun, move and interact through their gravitational forces. For Pluto, this issue highlights how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex manner. Terms such as asymmetric libration, scope libration, and VZK wobbling are key to unraveling this puzzle. According to astrophysicists, what keeps Pluto and other planets in their orbits is a form of libration. In the case of Pluto and Neptune, this term means that when Pluto crosses Neptune's orbit, their positions are typically separated by at least 90 degrees. This spatial separation is crucial in preventing their orbits from interfering with each other. Vertical libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or other giant planets, it is positioned far above their orbital plane, providing an additional layer of protection against potential collisions. Another critical factor is the VZK wobbling, named after three scientists, Vaisala Kozai and others, who studied gravitational influences on orbital motion. This phenomenon explains why Pluto's orbit remains stable despite its apparent chaos. These intricate interactions demonstrate that despite appearances, Pluto's orbit is governed by patterns and forces that maintain long-term stability. Mathematical simulations from the late 1980s revealed that, despite its irregularities, Pluto's orbit is remarkably stable over extended periods. Small changes in initial conditions can lead to significant differences, but overall, the orbit remains consistent. Further computer models have shown how the gravitational forces of giant planets like Neptune, Jupiter, and Saturn help stabilize Pluto's orbit around the Sun. Neptune and Pluto share a unique orbital relationship. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance prevents collisions by keeping their orbits synchronized. Jupiter's immense gravity also plays a critical role in stabilizing Pluto's trajectory, preventing it from being ejected from the solar system. Astrophysicists like Neil deGrasse Tyson have drawn attention to the complexity and fragility of this delicate balance. Tyson, known for reclassifying Pluto as a dwarf planet, highlights its irregular orbit as a fascinating case study in celestial mechanics. He emphasizes that while Pluto's orbit is stable for now, subtle changes could disrupt this equilibrium in the future. In summary, the interplay of gravitational forces among Pluto, Neptune, and other planets ensures that their orbits remain stable over billions of years. However, the possibility of disruption serves as a reminder of the dynamic and ever-evolving nature of our universe. Understanding Pluto's journey helps us appreciate the intricate balance that governs our solar system, offering valuable insights into the mysteries of the cosmos. The concept of orbital resonance, particularly the 2:3 relationship between Pluto and Neptune, is a key factor in understanding the stability of Pluto's orbit. This resonance is not just a coincidence. It is a result of billions of years of gravitational interactions between the two bodies. For every 2 orbits Pluto completes, Neptune completes 3, ensuring that their closest approaches never result in a collision. This delicate dance is a testament to the power of gravitational forces in shaping and maintaining the structure of our solar system. Despite this stability, astrophysicists like Neil deGrasse Tyson and Michio Kaku warn that the future of Pluto's orbit is not entirely guaranteed. While the resonance has held steady for billions of years, the chaotic nature of celestial mechanics means that even minor changes in the positions or velocities of planets can lead to significant alterations over time. For example, interactions with other planets, such as Jupiter and Saturn, could introduce perturbations that destabilize Pluto's orbit, potentially increasing the risk of a collision with Neptune. Such a collision, though extremely unlikely in the near future, would have catastrophic consequences for the solar system. The immense energy released by the impact would not only affect the 2 planets involved, but could also disrupt the orbits of nearby celestial bodies. Fragments from the collision could be ejected into the inner solar system, posing a threat to Earth and other planets. This hypothetical scenario underscores the importance of continued observation and modeling to understand and predict the long-term behavior of celestial bodies. Moreover, the study of Pluto's orbit provides valuable insights into the broader dynamics of the universe. The principles of orbital resonance, gravitational interactions, and celestial mechanics observed in our solar system are also at play in distant star systems and galaxies. By studying Pluto and its interactions with Neptune, astronomers can gain a better understanding of how planetary systems form, evolve, and maintain stability over time. Pluto's orbit also serves as a reminder of the limitations of our current knowledge. While mathematical models and computer simulations have greatly improved our understanding of celestial mechanics, they are not infallible. Small errors in initial conditions or simplifications in modeling can lead to significant discrepancies in predictions. This uncertainty highlights the need for continued research and technological advancements to refine our understanding of the cosmos. As we look to the future, the study of Pluto and its interactions with Neptune will remain a crucial area of research. Advances in technology, such as more powerful telescopes and improved computational models, will allow astronomers to delve deeper into the mysteries of Pluto's orbit and the forces that govern its stability. These efforts will not only enhance our understanding of Pluto, but also contribute to our broader knowledge of the universe and our place within it. In the end, Pluto's story is one of resilience and adaptation. Once demoted from its status as the 9th planet of our solar system, Pluto continues to capture the imagination of scientists and the public alike. Its complex orbit, shaped by the gravitational forces of its neighbors, serves as a testament to the intricate and dynamic nature of the cosmos. As we continue to study Pluto and its relationship with Neptune, we are reminded of the delicate balance that sustains our solar system and the boundless mysteries that await discovery in the vast expanse of space. As Pluto's orbital stability continues to captivate astronomers, the broader implications for understanding celestial dynamics grow increasingly significant. The delicate gravitational ballet between Pluto, Neptune, and the larger planets like Jupiter and Saturn highlights the role of interplanetary interactions in shaping the solar system's architecture. Without these stabilizing influences, chaotic events such as planetary collisions or ejections might be far more common. The concept of orbital resonance, particularly in Pluto's case, has inspired deeper investigations into similar phenomena elsewhere in the universe. For instance, exoplanetary systems around distant stars often display resonances that hint at the forces that govern their formation. These patterns provide clues about how planets migrate during their early histories and how their interactions influence the long-term stability of their systems. By studying Pluto and Neptune, astronomers can refine models to apply to other systems, advancing our understanding of planetary evolution across the cosmos. The hypothetical scenario of a collision between Pluto and Neptune is not merely a thought experiment. It also serves as a warning about the fragility of cosmic equilibrium. Though such a collision is highly improbable due to their resonance, it draws attention to the dynamic nature of celestial mechanics. In extreme cases, even small perturbations in the system could trigger cascading effects, destabilizing other planetary orbits. Understanding these dynamics is crucial for modeling the future of our solar system, especially as gravitational interactions evolve over billions of years. One area of growing interest is the role of external forces on the solar system's stability. The gravitational pull of passing stars, or even the influence of the hypothetical Planet 9, could introduce changes to the orbits of distant objects like Pluto. These forces, though subtle, could accumulate over time, leading to significant shifts in the solar system's configuration. Studying how such influences might affect Pluto's orbit and its interactions with Neptune offers valuable insights into the resilience of our solar system in the face of external disturbances. Pluto's unique position as a Kuiper Belt object also sheds light on the broader population of icy bodies beyond Neptune. These distant objects, remnants from the early solar system, share similar orbital characteristics with Pluto, including eccentric and inclined paths. By studying Pluto as a case study, astronomers can better understand the dynamics of the Kuiper Belt as a whole, including the processes that shape its structure and the potential for collisions among its members. Additionally, ongoing research into Pluto's internal structure and composition reveals new dimensions to its story. Data from NASA's New Horizons mission showed that Pluto is a geologically active world with features such as icy plains, towering mountains, and potential subsurface oceans. These discoveries suggest that despite its small size and distance from the Sun, Pluto is far from a frozen, inert body. Its active geology may influence its orbital evolution over time, as internal processes like cryovolcanism or shifts in mass distribution affect its gravitational interactions. Astrophysicists like Neil deGrasse Tyson emphasize that the reclassification of Pluto as a dwarf planet should not diminish its importance. Instead, it highlights the need to expand our understanding of the diverse range of celestial objects that populate the solar system. Pluto's story, from its discovery to its ongoing study, exemplifies the dynamic and ever-evolving nature of astronomy as a science. As technology advances, future missions to the Kuiper Belt may provide even more detailed data about Pluto and its neighbors. These missions could unlock new mysteries about the origins and evolution of our solar system, offering a clearer picture of how distant objects like Pluto fit into the larger cosmic puzzle. Ultimately, the potential for a Pluto-Neptune collision serves as a powerful reminder of the complexity and beauty of the universe. It underscores the need for continued exploration and observation, not only to safeguard our understanding of the solar system, but also to inspire curiosity and wonder about the vast, interconnected web of forces that shape our existence.